Hello, everybody. I'm Wyatt.
I'm Ryle.
And, we're here to talk about running a node for a distributed ledger. So this is the part where we talk about ourselves. I'm Wyatt. I'm the CTO. A little bit of background. I started my career in the South Bay doing research at NASA Ames. I was a physics guy, but I got into ML by writing an algorithm to classify whether or not a stream of information contains some kind of, animal or whatever communication, a la aliens. Did some stuff in quantum computing. I got hired by this guy after college doing machine learning, and I've been working in the distributed system space, just trying to scale machine learning algorithms ever since. Yeah.
I'm Ryle Gohausen. I'm VP of Engineering. A little bit of background on me. I come from Salesforce, where I was doing performance engineering on machine learning at scale. I was part of the Einstein project, which is a new initiative there for doing machine learning. I've worked on products for Marketing Cloud, Einstein engagement scoring, Service Cloud, and case classification. And I'm a contributor to Transmogrify AI, which is a new auto ML machine learning application developed by Salesforce, built on top of Spark, which is the largest MapReduce framework. Before that, I was working as a data scientist at Radius, where I met Wyatt. And I've also been working with Spark and MapReduce and distributed computing for many years before that. I was one of the earliest testers of Databricks, which is the commercial monetization of the open source Spark project. Spark is viewed as the sort of spiritual successor to Hadoop, and it's pretty much the most popular MapReduce implementation today.
So this is a brief overview of what we're going to be chatting about today. Ryle's going to kick it off for the first half, sort of breaking it down like where we are right now in the space, where we came from. I'm going to talk a bit about Constellation and what makes us different, and then we're going to do a little demo tutorial thing. I'm going to show part of something that we've implemented since our last talk, which is a reactive validation pipeline. Ryle's going to go through some of our tools and like our deployment process. Kick it off.
So what is Constellation? Why are we here? We're trying to solve enterprise-grade decentralized applications. You may have heard of DAG technology. It's basically a way of breaking up blocks into smaller quantities and figuring out a way to correctly parallelize the problem. Synchronous blocks don't work. They don't work at scale. They're not how MapReduce works or distributed aggregation systems works. There's also a huge problem in platformization. They talked earlier about this centralization trend among decentralized networks, which is crazy. As they become larger, they become more centralized. It's, in our view, more important to focus on disparate networks, federation, integrating different types of networks, and microservices angle as an approach. AWS does not have a completely unified platform where you have to do everything a particular way. They offer plugins and customization to a developer. S3 and EMR are isolated microservices. That's what enterprise expects in the computing and infrastructure space. And really, there's not been a great application development lifecycle for blockchain. Everybody is coming into it expecting it to be like developing on AWS, and it's just, it's not. It doesn't work that way right now. So for those of you who might be a little unfamiliar with blockchain, or at least the evolution of the space, it started off with securing transactions and ledgers. And it moved into digital contracts, and finally, it's trying to solve the problem of applications. So all of these things essentially boil down to an observation chain that's cryptographically secured. Bitcoin is now just considered as an application of some sort of underlying protocol. And if you might ask, why build apps on a decentralized thing? Why not just use AWS? AI now is being viewed as sort of in the same realm of electricity, but I think it's more fundamental that we talk about securing infrastructure. If you're talking about oppressive governments or middlemen or business interests with conflicts or monopolies, most people don't view Amazon very favorably right now. And these things are completely anti-decentralized. And they don't really provide a form of security that's auditable. And there are no regulations around cloud computing for the most part. We see this sort of trend of adoption of taking contracts out of the regular legal form in the form of SLAs. There should be ways of testing applications to see if they're actually working and codifying that into digital form. And that's not really done right now very well, although that's sort of the direction this space is headed for. So the current limitations that we want to address are finite block sizes, blocks that don't just consist of partition blocks, which is basically the suggestion for fixing the performance problem, but it doesn't really consider what happens across different networks. Obviously, resource waste, redundant work, running application code over and over. You can't really host a modern application on Ethereum. You couldn't serve a website. You couldn't really serve a scalable database. It wouldn't work. These networks can't connect. Again, you're locked into that abstraction. You can't start a competing version of Ethereum. You use exactly what they offer you, and you have to fit inside their sandbox instead of integrating, which is not what we want to go for. There's no throughput to speak of. And in addition to all of this, all of these approaches that have on-chain data management or data embedded in contracts get into legal issues. Right? GDPR has modified the way every enterprise is dealing with customer data. And not just that, but there's also potentially illegal content, all sorts of issues associated with these platformized approach, which essentially require you to follow X, Y, and Z instead of trying to integrate different services. This is a basic demo for those of you unfamiliar of what the visualization of these blocks. You have a synchronous ledger state. Everyone knows about it. There are fixed blocks that update them. That is not really an asynchronous processing paradigm. Right, so we're going to talk a little bit about the debate in the ecosystem. This isn't our criticism alone. Plenty of people have talked about Ethereum going towards too much centrality. And it probably is in part due to how much money and attention that they have raised. And sort of trying to push the bar, past what Bitcoin can actually offer. So this criticism has been made not just by us, but also by Hyperledger, Interledger, Cosmos and Polkadot are also leveraging similar criticisms. When you think about what blockchain is, it's a way of securing updates to a global database. And if you talk about enterprise grade, you need to look at what AWS does for a security model, right? AWS's security model doesn't enforce security to the degree that it forces you into only using certain solutions. It's designed to empower all sorts of different solutions, which means consensus is the underlying problem. Ethereum, when it undergoes contract updates, we're using Ethereum as a standard example because everyone is mostly familiar with it. When it undergoes these contract updates, they eventually come to consensus on the results of the state transitions in the form of hashes or ledger updates, which are very, very simple to understand. That pattern can be extended and focused on in isolation as a service layer abstraction. There should be a proper boundary created so that you could use varying VMs or contract languages that might be suited to different platforms, running on a cell phone, running in the cloud, running on a home computer. These are all different heterogeneous environments. And this would be sort of like using a storage service that only worked with Python. It's an improper abstraction, and it's really designed to fuel speculation. This doesn't really reward people for developing separate solutions. You can't have these, these protocols have sort of taken on so much ground that they can't really solve anything. So when we're talking about this, we're interested in microservices, more approaching this from an angle as a tracker across different services. If you can solve consensus at scale, there are any number of plug-and-play components that you can incorporate from other projects, which is far more interesting from a decentralization perspective. We're interested in networks reinforcing one another rather than dictating what you have to do. So this is the most common criticism you'll see, which is more of a historical description of what happened with the development of blockchain, is protocols forced so much effort into the security that they sacrificed all of the performance up front. This basically means you can't have competitors for a lot of these things. You can't have competing VMs. You can't have competing execution providers. You can't deal with people who don't want to run code from other people. Every node needs to run all of the applications. And in addition to this, why would you build an application on one of these protocols when all you're really doing is enriching the creators of that protocol? It's an unfair balance. And it avoids all of these issues of integrating properly and building a community if all of the value is driven into the protocol. So again, you see the issue with these large protocols is they have to run all of the applications inside of them. They don't have application separations and boundaries between them. This also creates data management concerns and issues. The way to abstract over this is to focus on isolating out consensus in and of itself as a service and focusing on the performance of that, because that happens anyways in the regular ecosystem. So our solution is, again, based strongly around DAGs, but we would rather rephrase this argument as being nonlinear. If you're talking about consensus across networks, there are not necessarily linear relationships. It doesn't boil down into here's a set of partitions, here is the data, here's an exact update to it. It's coarse, it's granular, it's graph-like in nature, and they're globally distributed networks. They're also, each application has its own unique pattern, access pattern for data dependencies and all these other issues. The huge thing here that doesn't get talked about is if you create a small network, it's not going to be secure, right? If there's been double spend attacks, any miner who has enough power can instantly destroy a small network. Anyone with enough state can manipulate their markets, and the consensus models don't reinforce one another. If you try and go out, it's anti-entrepreneurial, right? You can't start your own network. You have to go to a large provider. If you have a new idea, you have to do what they say. You can't just create a network and try and integrate it with something because they don't trade resources fairly. There is a marketplace, and there are attackers out there, and there is nothing that allows these networks to trade security with one another and reinforce each other fairly. So some discussion on what is out there in consensus right now. Proof of work, obviously the original. The origins are in anti-spam for email. It was originally used for small capacities. It would basically the death by 1,000 cuts. You send out a large amount of computation. It becomes cost prohibitive to spam a large number of people. These double spends are in the news all the time on smaller networks. It doesn't work. It's a known vulnerability. Yes, it may work in some crazy situation where you have this economic incentive. There's an argument out there to be made for that, but it's not necessarily going to hold. Proof of stake, yes, it addressed wastefulness. You still have vulnerabilities. People have manipulated smaller proof of stake coins. It happens all the time. These networks get attacked. And in addition to that, it's not really a good philosophy. We don't run the world by trusting people just because they have money, right? That's not democratic. That's not a governance solution. And this goes beyond just validating individual transactions and having penalties. It's more about the governance of the entire protocol itself. You can't rely solely on buying votes. That would be considered absurd in the real world. So reputation and trust, it's already conventional, right? This is credit scores. This is auditing. This is accounting, finance. This is considered normal. There's not yet been a strong evolution in this. Like, the eventual use case of digital contracts is to replace legal contracts with code as law philosophy. There is an enormous amount of machine learning that can be done. Who are the people involved in these things? Where are their IPs coming from? All sorts of off-chain data that can be integrated very, very quickly and easily. So far, that really hasn't happened. You look at Ripple, and they let you select from a set of validators. That's the bare minimum of reputation and trust. They've barely even gotten started. Network effects are super important in securing networks. We're talking about things like measuring the equivalence of measuring influence on Twitter to figure out who you should follow or how your feed is informed. Network effects exhibit, from a small scale set of rules, a gradual buildup of something powerful. If you know someone else who is trustworthy, the people that they follow are more likely to be trustworthy, and so on. There are transitive and associative effects that are well demonstrated in research. You can read about Facebook studies on social networks and how there are associative properties that line up in social networks, which in cumulative effect lead to trust. This is how we trust news sources today. You don't trust someone just because they have money or some other effect. Things develop a following over time. And right now there's a massive level of ignorance about what happens in the code publishing process, who governs the project itself, right? All of these steps require trust, and they just ignore it completely. We need to go towards democratic governance, not buying votes.
Cool. Thanks, man. I thought that was pretty cool. All right, so I'm going to take over real quick. Yeah, thanks. Give it up for Ryle. Just breaking it down. Thanks, man. All right, everybody. So we're about to talk about Constellation and how we're doing things a little bit differently. So right here, I just have a quick breakdown of a couple of the pillars that we have that kind of make us different, and sort of how we're able to integrate with the technologies that make things actually consumer and enterprise ready. So yeah, just starting off, case in point, we are quite literally as nonlinear as a graph. Our underlying data model is a data dependency graph that is made up of cross-link signatures. What does that actually mean? Let's break it down in terms of what we talked about just a second ago. We have your notion of a linear chain. Every node maintains the total state of the network. They come to agreement on the state of one tiny, limited-sized block. In our situation, because we have a structure like this, we do not have to keep the total state of the network on every node. We do not need to have every node know about every other node. That sounds kind of like the architectures that we would expect for, like a big data application or something like HDFS. This is basically just a much more efficient way of keeping track of stuff and rebalancing data across the network. This really touches into something I'll mention later about data locality. Basically, when we want to actually perform data intensive, very intensive computations on some network, you don't want to send data around. You just want to send the computation and allow the nodes to govern where data should be formed. This underlying structure is indicative of something that can do that. One other thing to break down too is from a security standpoint, the ability to forge multiple signatures cross-linked across a very large diameter in a network is exponentially more difficult than just doing it on a linear chain. Straight up. And there are not only that, like our number one thing we've used to describe sort of where we are and where we're going is Ethereum, and there has been a lot of work towards this. I'm not going to plug other stuff, but a pretty simple Google will take you to some of the work by Leslie Lamport and other people who have solved the issue of 99% fault-tolerant consensus. Yeah. So like I said, this allows us to use some existing technologies and stuff that's used for data-intensive applications. Basically, what you're looking at right here is some of the stuff that, this is our stack. We're trying to repurpose all the tools that Twitter used in order to do machine learning on the fire hose. Straight up, we have Minhasher 32 right here of how we're going to apply this to our own dynamic partitioning and just doing approximate lookups. That allows us to do things, once again, exponentially faster and with the same level of performance that you'd expect from someone who's building a backend like Facebook or Google or the stuff that you use every day. So yeah, in addition to that, some of this, so we're starting to also move a little bit towards another thing that we have managed to sort of solve or have an approach to solving, which is liquidity. And this is going to come into that in the next slides. So yeah, moving into that. Right. So before I move on to the other aspects, I'm going to talk a little bit about our consensus model. Ryle had a great breakdown sort of the current state of, hey, should we just trust some dude who has a ton of money, or should we actually try to apply some sort of a real, meritocratic way, if you will, of governing ourselves. Who's just going to leave it up to something like stake, right? So basically, we have this approach called proof of reputable observation, originally called proof of mean, but we decided to move it to something that actually translates directly to our own code base. And this whole thing just boils down to the more transactions are observed, the more valid they tend to be. And not only that, cross-linkages themselves act as cross-references, referentiability from the viewpoint of the observers of the network. Any node can sort of see what other nodes are doing, and by cross-checking all the activity, it allows us to create a really robust audit trail. That is very hard to forge. Cool. So getting a little bit into how we're handling scalability and sort of that liquidity problem, we're going to talk a little bit about the network structure. So here we have, I think I'll just start with the example in this take. I have this thing called stochastic neural gas. This is something quite a bit different than our own network. It's an algorithm that is trying to find its own sort of like space versus volume constraints. It's trying to find the most optimal topology to fill a space. Bit different than ours, but I can tell you that that is what our network is going to look like as it repartitions itself over time. So as I mentioned before, the issue with data locality is sort of central to building scalable applications. How can I host data in an efficient way that lookups don't take a ton of time and don't crash my entire network? That is sort of the fundamental problem that has been solved in the last 10 years in building these scalable, horizontally scalable solutions. That's exactly what we did here. And what we do is we apply something called normalization, use normalization in our dynamic partitioning scheme in order to create something that's like a scale-free network. You can see down here on the left, that is a normalization into a hyperbolic space, which has one of these properties of this kind of an algorithm, which can then actually find an optimal topology for hosting your data. This is the stuff that happens under the hood when you're like, how am I downloading all these things on BitTorrent or whatever, in any kind of torrent system? They're able to handle locality and have some kind of partitioning scheme like this. So obviously, if we're going to achieve some notion of dynamic partitioning like this, we need a data model or a data structure that is reflective of that. And thus, we have a hierarchical data structure that is made up of signed observation edges, made up of transactions and other edges, that recursively define themselves. An observation edge of an observation edge would become a depth level 2 node inside this type of a topology you can see. So looking at this kind of dendrite structure, you can see the outer nodes are going to be something like just a validator witness node, and something all the way on the inside, something very deep, is going to encapsulate a view that has the entire perspective of the whole network. So if you take a look at the center of the dendrite on the top, the center has a view of everything around it, but from the outside's perspective, it just has a view of what's local to it, and it also has an understanding of the total network, but just from a few steps behind. That's all that's necessary. That's really all that's necessary in order to apply some kind of an efficient validation. And that's sort of how we're able to have some of those, some optimizations. So yeah, this is kind of, this is what is required for us to actually build a data model, data structure that will allow for that scale-free network to just come out. Cool. So I have a little bit of a breakdown. This is going to be something I'm going to talk about in my demo, but basically the way in which our data is processed could be characterized as like asynchronous. Basically, we have a pipeline, a validation pipeline, where data goes through and it is handled by some asynchronous process that doesn't necessarily rely on somebody else. So in that sense, you can see sort of as we're scaling down this axis, I might have one process on a depth level 1. I might have a process on depth level 2 that's reliant on depth level 1. All of those processes can actually happen at the same time. So that path, if you were to follow the red line from the top there all the way down to the bottom, all of those different components that need to happen all happen on their own cadence, basically. We don't necessarily need to wait for an entire network to synchronize in order to have our network display the effect or to update itself. And as you can see at the bottom, this is basically a DHT. I mean, if you look at BitTorrent or some of the things we're doing to build those types of systems, just sort of a rehashing of that. So yeah, essentially this whole thing is a reactive execution graph. A future or some type of a process that is managing operations can then call off other processes, and they will self-manage themselves, returning the final result that you actually need. So from the perspective of actual execution, everything just happens implicitly. So I just wanted to touch a little bit on our approach to building apps with Constellation. So just from a perspective of having different depths running the same sort of protocol on recursive data, it's sort of basically the way we are handling scalability is the same way you will build your own dApp. So if you take a look at this demonstration or this the world's best diagram ever. I apologize, but it's going to do its job for today. Take a look at our handy-dandy pentagram. Of course, it's a pentagram because we're dealing with networks and Metcalfe's law. If you take a look at that red line, which can partition both that linear chain and that pentagram, one could actually conceptualize what a distributed application will look like. That actual structure at the bottom, which is made up of these different denoted, these circles that are made up of N6 whatever, could be considered a process, let's say that's like bread token. That bread token could be made up of water token, yeast token, flour token, and thus to maintain some sort of connection to the greater network, provide resources to some depth in the greater ecosystem. That is actually how we're going to achieve cross-chain liquidity, by sharing resources across different depths in that network. How is that actually possible with all the issues we've heard about cross-chain atomic swaps, or even the fact that we don't even have most other chains, or anything I've seen, has a real answer to how to store or reference physical real-world data on chain? We handle this using data normalization, the same techniques we use in order to get data sets to commute together to form some machine learning model. We do the same thing to make sure that chains can talk the same language. If you can talk the same language, you can reference each other in the same way we would call an atomic swap. Cool. So I just wanted to take this a little bit further. So with that metaphor that I mentioned before about like bread token, each one of these different, what we're calling parachains could sort of be seen as like its own commodity. I mean, really, what is the value in a utility token? Right. I mean, if you can't define utility, if you can't actually define a physical metric that represents that utility, it's not a utility token, right? So this whole thing actually opens up. Like Constellation's ecosystem is really kind of like a decentralized exchange of all of these digital commodities that are starting to form. Whether or not it's like basic attention token, whether or not it's going to be something connected to like a sensor network or something somewhere. What we really want to do is make sure that real world value is referenced by these tokens, and that they can be traded referentially, in the same sense that like 1 calorie might be equal to X ergs of energy with some kind of like parachain connection. So this really just allows us to actually create a liquidity situation that isn't really there right now. If I have tokens and I want to, let's imagine we're at the point where we can start using these cryptos in our real day-to-day life. What am I going to do? Take all my crypto every morning, go to an exchange, move it over to another thing, worry about some other like fluctuation, do something else? No, you want to have the same Apple Pay-like consumer experience. You want all your tokens in one place, and you want every single token to be equal to one another in some way. The ability to transfer value across these different chains. That's what this is going to look like, and just reusing the data normalization approaches that we need to make complex machine learning algorithms, namely a data normalization that's topologically invariant. I'll leave that for another talk. That's going to be possible.